This next section has to do with key ideas and terminology in probability and statistics. And one of the big ideas in the field of statistics that's a little bit different than the field of mathematics is that in statistics, context is very important. If you have a list of numbers that represents collected data, then that data is always collected in some sort of context. We've had different contexts up here. One of them was the number of spots on a Dalmatian. The context can be anything, but in statistics, that context is important and usually needs to be attended to at some point in the solution. In mathematics, that's not always the case. In fact, sometimes if you're doing a mathematics problem, you may want to strip the context from the numbers just to focus on what's happening with the abstract numbers and the patterns that may exist there. But in statistics, context is important, I think, as this next example shows. So this is an example problem that says Carlotta wants to display this data in a circle graph, and then it gives us some numbers, 19, 16, 22, and so on. It says, what is the measure of the largest central angle needed? And that's it. This is a hard problem to figure out necessarily what's wanted, and I believe it actually comes with a circle graph drawn like this as part of it, and this is just asking what's the measure of the largest central angle needed. There's not a whole lot of context here. The largest central angle needed for what? To display this data to show what? What do these numbers mean and where do they come from and how are we supposed to make sense of it to make the circle graph? So this is a hard one, and I'm just kind of stuck with imagining that they probably want us to add up all of these numbers, realize that 54 is the largest number, and then take 54 divided by their sum. Or I think if we add all of these numbers up, they add to 160. So 54 divided by 160 is equal to 0.3375. And then to figure out the angle that's needed for that piece of the pie, we would multiply 0.3375 times 360 degrees, and then that would give us the answer. But again, this is a great example of a difficult problem, not necessarily because the idea is difficult, but since they didn't give us enough context, it makes it kind of hard to read their mind, the question writer's mind. Another key idea in probability and statistics is the idea that, in particular in statistics, often we're trying to measure uncertainty. And that's kind of tricky. We have this thing that's going to happen in the future, and we're not quite sure how it's going to turn out, but we think that this probably will go this way, but it might go the other way. And so we're trying to measure the uncertainty or quantify it in some way. And so this brings us to a key concept in probability and statistics, as is exemplified in this next question. This one says, your math bowl coach tells you there is an 80% chance that snow will cancel our practice tomorrow. Which of these statements describes what your math bowl coach is saying? Is the coach saying there is definitely no practice tomorrow? It is likely that there will be no practice tomorrow. It is unlikely that there will be no practice tomorrow, or it's impossible that practice will be canceled tomorrow. So this is kind of tricky, this idea of 80% chance that something's going to happen. So we need to think through this in terms of probability. If something has a probability of 1, then that means it's definitely going to happen. If something has a probability of 0, then that means it's definitely not going to happen. But if something has a probability of 80%, well, it's more likely to happen than not. So there's a good chance that whatever's being predicted is likely going to happen, but it's not a sure thing. So that's this key idea of somehow trying to measure uncertainty with the idea of chance. This next question is another key concept in probability. And this one is an often, it's a misconception that often occurs among students and adults alike. this question brings out the misconception that's usually there. So let me go ahead and read it. This one says, Florinda tossed a fair coin 5 times, and it landed with heads, 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 tails, and tails facing up. What is the probability that tails will face up on the 6th toss? So they give you a coin flip, is the context, and they flipped a coin 5 times, and they give you the history of what happened in those 5 flips. But the question asks, what is the probability that the next toss will be a heads? And when you're just focusing on the probability of what's going to happen next, and only what's going to happen next, then the probability is 50-50 chance. There's a 50 chance it will be heads, 50 chance it will be tails. Now, if the question somehow ties to the stuff that happened before, then it can become a more complicated problem. But the way this reads, they give you a history, but then the question they ask doesn't have anything to do with that history, and they just say, what's the probability that the next flip will be tails? And so it's going to be 1 out of 2. All right, this next question ties to the coin toss problem that we just discussed. It says, if the spinner is spun 12 times, what is the probability of spinning a diamond on the last spin? So here again, it says the spinner has been spun 12 times, but then the question just asks what's going to happen on the last spin. So the question doesn't really tie in what's happened to the past. So with this one, this again ties to key concepts in statistics because this is one where a misconception often comes up and causes students to get the problem wrong. With this one, it's just, what's the probability you're going to get diamond on the last spin? Well, if you spin on this spinner, looks like half the time you're going to get diamond, and the other half you won't. So there's a 1 out of 2 chance that will happen. Well, this next question has to do with some key terms in statistics, and this question, it falls into the category of being an informal inference question. So let's look at it. Your school has 550 students. You asked 50 of them if they prefer chocolate ice cream or vanilla ice cream. Of those 50 students, 62% chose chocolate. If you polled the whole school, about how many would you expect to select chocolate as their favorite flavor? So with this question, you have this idea of a larger group. I'll just represent them with a big circle, a whole bunch of people in here. Actually 550 people. The number of students in the whole school, and there are 550 of them. We call that larger group the population. And then, rather than trying to ask all 550 of them the question about ice cream, they pull out 50 and then ask the question to these 50. And so this smaller subset of the larger population is called the sample. And then they ask the question of the sample and find that 62% of the sample said that they would like chocolate. And then here's the kicker. If this sample represents the population well, if this sample really does look like the larger population, then we could assume that this 62% in the sample is similar to what's happening in the population. So we could say, well, probably about 62% of the population feels that way as well. The difficulty is making sure that you take your sample in such a way that it is representative of the whole population, and that's kind of beyond the scope of these talks. But let's go ahead and make that assumption that this sample looks like the larger population. Then we can use this idea of saying that this 62% will also happen over here in the larger population. That's called making an inference. We're inferring that this 62% holds for the bigger population as well. So to answer the question about how many students would you expect to say in the larger population that they like chocolate, it would be 62% of 550. So if you make that multiplication, I believe that it turns out to be 341. Okay, so this next problem reads, if Eddie spins the spinner 32 times, he would expect it to land on what? Either a vowel twice as often as a constant, E twice as often as X, M twice as often as X, or X twice as often as M. So let's look at what's happening with this spinner. And a key idea here, it's saying that he spins it 32 times. So that number's starting to be a big number. What happens if he spins this over and over and over and over again? So here's the spinner. And in this spinner, we could ask ourselves, what's the likelihood that he would get an E? Well, if you spin this, there are 8 equal-sized pieces of this spinner, and there are 3 of them that are an E. So there's a 3 out of 8 possibility, or a 3 out of 8 probability that he would get an E. How about this question asked about vowels? For here, there are 1, 2, 3, 4 vowels. So the probability that they'll spin a vowel is 4 out of 8, or 50%. So with this one, the theoretical probability that you would get a vowel is 4 out of 8. So a key idea in this problem is that if this is what's happening theoretically, just looking at the sizes and thinking through what would happen on one spin and what should happen if everything's fair, we can move to this idea of empirical probability of what's going to happen if we do this experiment over and over and over and over again. And the law of large numbers is a key concept in statistics that if you do something enough times, then the empirical probability of what happens if you do the experiment over and over and over and over and over again, that empirical probability will approach the theoretical probability. So that the likelihood that you would get a vowel, about the same number of times as you would get a consonant. Okay, so in this one, the first possibility would be out. Since there's a 50-50 chance of getting a vowel, then that means you would have a 50-50 chance of getting a consonant. So there would be the same probability of getting both of those, and part A says you would get a vowel twice as often as a consonant. So that one's out. How about E? Would you get E twice as often as X? Well, there are 3 ways to get an E and just 2 ways to get an X. So again, using this idea of the law of large numbers and the empirical probability approaching the theoretical probability, this is 3/8 for an E and 2/8 or 1/4 for X. So that one's out. It looks like C is out, M as often as X, because there's just one M and there are 2 X's. This last one, X twice as often as M. Well, there are 2 out of 8 possibilities of getting X and 1 out of 8 possibility of getting an M. So it looks like the probability you would expect to get X twice as often as you would M. This ties together some nice ideas, some big ideas of the law of large numbers, empirical probability, and theoretical probability. So this is a good question.